going to talk about the unit circle. A unit circle is a circle on our Cartesian plane. Now, can I draw nice circles with this program? I'm not sure I can. Which is not going to be nice because I never do a good job at this. I'll do my best here. 1, 2, 3, 4, 5. Oops. This is my best attempt here at a circle. I'm right now trying to give myself anchors. I visually can do this, but I do not have the dexterity to do this well. As poor as this looks, that's one of my better attempts at it. This the first quadrant's in rough shape. Maybe I'll redo the first quadrant. Okay, but while I do that, let's talk about the unit circle. So unit circle, the reason I call it a unit circle is the idea is that you can convert it to have a radius of any units. The idea is that the radius of this circle, okay, is exactly, let me go to the outside, it is 1 unit long. So this radius is 1, okay? And what happens is you can move it all the way around, the radius always stays the same. What's interesting about this unit circle is that we can use some of our previous information about special triangles to gather a bunch of the measurements and coordinates on this unit circle. So I'm going to make 2 of our special triangles for reference on the side, and then what we'll do is we'll use some graphing software to help make sense of it. So like we said, we got 45 degrees. Now, I'll tell you that the unit circle very quickly turns into measurements with radians. We'll stick it in degrees because that's what you're used to, but as you go farther in math, radians is the common measurement for this. And a radian has to do, I'll quickly touch on this. A radian is actually a radius. So like I said, this radius is 1, and technically from here to here is also 1. If I happen to be at what is considered a radian, this measurement around the arc is also 1. It's the idea that this measurement around the arc is the same as the radius of the circle, so they call this 1 radian or 1 rad, for example. Now they'll usually use, if you've ever seen it before, they'll use like pi over 2 for 90. Is that familiar to you? No, not at all. Okay, we'll stick away from that. It'll come up eventually for you in math, okay? Let's go back to our degrees. Our other measurements here are 30 degrees and 60 degrees and 90. Our opposite sides are 1 root 3 and 2, and this one here gives us 1 root 2. Now, these special triangles, we actually want to fit them into here, okay? We want to fit them within this unit circle. Our challenge is, though, is this is essentially a hypotenuse. If we want to create little triangles, so let's say I make triangles like this, one like this, okay? This long hand here, this is the hypotenuse. Neither of our hypotenuses are 1. So that's what we talked about in the last one. The goal here is actually to scale this down. We're going to scale these 2 triangles down, which we've done before, so I'm going to quickly write them out. Just so we have them as a reference. We'll do them in red so that we know these are scaled versions that are supposed to fit inside the unit circle. If you ever see like an image of unit circle on the internet, they'll have a ton of information. There'll be coordinates and radians and degrees and radicals as the coordinates and measurements. It's tricky, but it's a lot of info from this one little thing. It's trying to give you a lot of info that you don't need to actually calculate. You can almost have like memorized if you know a few facts about math. Our degrees will always stay the same when we scale a triangle. That's the key about them. It's a really neat fact about triangles is our degrees, nothing changes. But if I need to turn this into 1, that means, like you said, we divide by root 2. So these 2 sides become root 2. And if I need 2 to become a 1, everything else is divided by 2. Root 3 over 2. Whoops. So, with that being said, what we can do is we can find some measurements. Let's assume that this is currently 45 degrees. And if we're talking about SOHCAHTOA, our primary trig ratios, this is 45 and this is 45, okay? We need to figure out the legs of this triangle, okay? Well, if this is 1, we're using this triangle here. This is our angle of reference, which means this opposite side, it also it's not 1, it's 1 over root 2 for the height of the triangle. And then the length of the triangle is also 1 over root 2. So if you notice, we fit that special triangle in there. because we're able to do that, this coordinate is actually, that's what your x value is equal to, and this is your y value. So this coordinate would be 1 over root 2, 1 over root 2. So you notice I've already put coordinates in here. And then sometimes they rationalize them. And if you remember when we did rationalizing, we just make it a regular 2 on the bottom. It ends up with like that. Okay, so sometimes you'll see like multiple versions of coordinates. Let's go to this side. This one here, this looks more like it was a 60 degree. I mean, it could be off. I could have not drawn it to scale, but what we're trying to do again is scale in our specific special triangles. Well, if the radius is 1, we already know that. I have my 60 degrees as my angle of reference. Opposite of my 60 degree is root 3 over 2. So opposite of this would be root 3 over 2. So that's the height of this triangle, which leaves the length or the width as a half. Now, my coordinate here would read like this, 1/2, and my y value be root 3 over 2, except that we're in the Cartesian plane. And in quadrant 1, yeah, all our coordinates are positive, but I'm in quadrant 2. So I've actually gone to the left with my x-axis. So my coordinate here would not be a positive coordinate, it would be a negative coordinate, which works out really nicely. I'm going to fit one more in here. We're going to do this, and then we're going to go and show like a dynamic view of this. Okay, same idea. We're going to use that same special triangle. Here's 90 degrees. This time the angle of reference is 30, okay? So we're in quadrant 3 here. We're going to have to remember some facts because 1 was easy, everything was positive. 2 a little bit. 3 is going to be a little trickier. The angle of reference, I know it's getting messy in the middle there, so maybe I'll change the color for this piece. It's 30 degrees, okay? We go back down to this triangle. Hypotenuse, still 1. That part never changes. But opposite of 30, that's actually going to be a half. So our height here is a half, which means our distance across must be root 3 over 2. Okay? So this coordinate is root 3, that's 3 over 2. And the height is a half, but we're in quadrant 3. In quadrant 3, our coordinates are all negative.
Yeah.
So the x value is negative and the y value is negative. Okay, that works out. Have you been taught or told about something called the CAST system? C-A-S-T.
He did go through it, but I was...
Okay. A stands for all, which means all trig ratios. All trig ratios are positive.
Mm-hmm.
In quadrant 2, S stands for sine. Only sine, represented usually this way, is positive. T, any guesses?
Total negative.
What about C? If you remember the 3 versions of it, you have all your trig ratios. There's sine, there's cosine, yeah, and then there's
tan.
yeah. Only tangent is positive in this one. And finally, only cosine is positive here. That's why we call it the CAST system. How do I go about proving this idea, or how do I kind of reconcile it? Well, I do this. I go, well, look at this information. This is my angle of reference. Sine is opposite. So sine, whatever my angle is opposite over hypotenuse. Well, my opposite is positive root 3 over 2, which is a positive value. So I'm just going to say, yeah, it's a positive value. And the hypotenuse is positive 1. That's also a positive value. Positive divided positive is a positive. I'm going to test my cos and see what happens in quadrant 2. Cos theta, I got to do my adjacent. Well, my adjacent side is my negative a half. So on top, my adjacent, I'm going to write these both out, is negative. But the hypotenuse is a positive. Negative divided by a positive, that gives me a negative. Oh, that makes sense. Cos is negative in that one. And same idea with tan, theta, opposite over adjacent. We already know the opposite's positive, but the adjacent's negative, and that takes control. That ends up being a negative. And you can do that with every quadrant, proving that, oh, that's why these things are positive, negative with your CAST system. So again, tons of information. And the unit circle actually holds even more, and that's why it gets so messy to look at. What I want to do, though, is I want to go through this idea.
Will the circle always be like radius 1 or will it?
So the idea is that the radius is 1, but let's jump back one more time. What's special about it is that you can scale it. That's why we started at 1 unit. Just like you took your triangles and scaled them down, we can take that circle and scale it much larger. Everything will be the same. Just like the angles being the same in a triangle. If this is just 1 unit for a radius, let's say this one is 2. everything in terms of length just gets multiplied by 2, right? Because really all we're doing is working with little triangles inside of it, okay? And that's where, again, this part you've never seen before, radians, that actually comes even more important when we're scaling triangles. It's the concept that the radius is always the same arc length, okay? As I scale a triangle, if I had a smaller one here, this is my radius, we'll say the blue part. My blue part here is the radius. Well, that would actually be the exact same length of this. So as I scale up, 1 radian never changes. It's the same portion of an entire circumference of a circle, no matter how big or small I scale it, just like we did with our special triangle scaling. Again, you'll get into that. So that's actually good to know eventually. I know you guys haven't quite touched on it. But the last thing I want to touch on is this piece. So here's the unit circle with some graphing software, much nicer than my renditions of it. What's nice about this is the idea is that we go around the circle. I wonder if I can do it. This guy, his values are, I'm going to label it. Yes, there it is. If I put play, you can see these values. Oh, why did I go to -10? Oh, okay, it doesn't matter. You can see those values going around. They become negative, one's positive, and they go back. Technically, okay, we can test some of these values. Remember we said one of them, what one did we test? We tested 45 degrees, and it was 1 over root 2, 1 over root 2. So A just happens to be 45 in here, okay? Is that 1 over root 2? I don't know, but I have a calculator. Let's give it a try. 1 over root 2, what is that equal to? Hey, that's that exact number. Except we don't write the decimals that way. They're a pain. We write them as these radicals here. Okay, so that one worked out. And then we went a little further, and we said, over here, this angle we put at, what do we say, 60. Now, the only thing I didn't touch on is if we're referring to, I gotta move this over a little. When we look at the unit circle, we're always talking about an angle from the origin, but in reality, what's actually, this is usually our angle of elevation. We're going from this platform. So if I want this internal angle to be 60 degrees, that actually means I'm looking for this angle to be 120. Okay, so in instance A, I would actually have to change that to 120 to be a 60-degree internal angle. So let's do that, and let's check if our information's right. Okay, I don't know if you recall, but our radicals there we said were -1/2 and positive root 3 over 2. -1/2 is -0.5. That worked out. Root 3 over 2, I don't know again. Let's find out. Root 3 divided by, oops, that's inside of it. Divided by 2, 0.866. Yeah, there it is. Okay, so those special triangles are nice because we don't have to actually use calculators to solve this. We just leave it as radical form. As long as we have them memorized, we're good. Yeah. The very last one, we might as well do it since we're here. I believe we said this internal angle at the origin was going to be 30 degrees. Well, if we let this run a little more, let's see what our angle actually needs to be. Our angle here is going to have to be something around there. In order to do that, we'll use blue maybe to get around. I got to go, ooh, I messed it up. There. I got to go from the beginning all the way around to here. Well, this is 180, and if I'm adding 30 more to it, that means this angle all the way around is going to be 210 degrees. I was so close when I stopped it. Let's go back. Let's change that to 210. And let's take a look. Oh, yeah, remember both were negative, but the two values had swapped? The exact same things that we had found with our special triangle. Okay.